Right, these are notes, examples, and thoughts on section 5.1 from your book, and we are going to be looking at how to differentiate the natural log function, ln of x. So let's start off by looking at this definition of natural log, and I would encourage you to try this out on your calculator just to prove to yourself that this works. Here's what I want you to do. Let's just test it out with something real basic. In your calculator, I want you to calculate ln of 5. I'll do the same thing here. So if you calculate ln of 5, you get approximately 1.609. And then if you apply this definition to the natural log, if we want to find ln of 5, that would be ln of 5, so the 5 in for x, equals the integral from 1 to 5 of 1 over t dt. So we should get the same number. So take a minute, use the Math 9 function on your calculator. And when you do that, you come up with 1.609. You should come up with the exact same number. So hopefully, at least in an intuitive sense, that proves to you that this definition right here is true. A real quick note here, it's good for you to understand, at least remember what the natural log function looks like when graphed. So here it is, there's your x and y axis. Natural log function is always increasing from left to right, passes through the point 1, 0, and takes on that basic shape. Okay, so if you think about the derivative of ln of x, let's again go back to this definition, and this should help us. So if we do ddx of ln of x, that would equal ddx, the integral from 1 to x of 1 over t dt. Well, if you look at this, hopefully you recognize that the right side of this equation is simply fundamental theorem of calculus part 2. And so when you apply fundamental theorem part 2, simply plug in the x here and for t, and you do have to multiply by the derivative of what you plugged in, but that's just 1. And so the derivative of ln of x is just 1 over x. Now, I'm sure you can understand that it would be a very rare situation when, you know, an AP test or one of my tests or quizzes is just simply going to ask you ln of x, or the derivative of ln of x. More frequently, you're going to have a composite function where u is something other than x, something a little more complicated. So I suppose it's a really similar pattern. Really, it's the exact same pattern. The derivative of ln of u is 1 over u, but according to the chain rule, you'd have to multiply by u prime. Often you'll see that rewritten as u prime over u, and that's a pattern we'll look for a lot when we start doing some integrals with this kind of thing. All right, so some examples here, and as always, I would encourage you to use your own notes, try these examples, and then watch the video, look and see how you did, fix anything that needs to be fixed, and hopefully learn as much as possible. Okay, here we go. Notice it's ln of u, so u is x squared plus 1. So I'm going to write this out as 1 over u, so it'd be 1 over x squared plus 1. You have to multiply by the derivative of what was on the inside. So the derivative of x squared is 2x. So you'd often see this written as 2x over x squared plus 1. Number 2. Again, this is ln of u, where u is something slightly complicated at least. So the derivative of ln of u is 1 over u. In this case, u is 3x. And you got to multiply by u prime, the derivative of what was on the inside. So the derivative of 3x is 3. So obviously this could be rewritten as 3 over 3x. The 3's just cancel here, and so you'd end up actually with just 1 over x for that one. Okay, the next few are going to get a little bit more complicated. Notice on the next one, ln happens to be the inside function. ln of x is on the inside of the to the 6th power function. So we're going to differentiate the outside first. So the derivative of something to the 6th is 6 times the inside. to the fifth. But then don't forget, you've got to multiply by the derivative of what was on the inside. So the derivative of ln of x, 1 over x. So you might see this written as something like 6 ln of x, quantity to the fifth, all divided by x, something like that. Okay, again, just a reminder, once you feel comfortable with these, maybe you're already there, feel free to pause the video, try it on your own, and then check how you did. Okay, a few more examples left here. Number 5. Number 5 is definitely the most complicated one we've looked at so far. Let me make sure, did I just skip one? I did, number 4. Let's do number 4 before we do number 5. All right, so number 4, do you recognize the rule? You see the product rule, right? We've got two different functions multiplied together, and we're supposed to differentiate those. And so, we're going to do the product rule. So, we're going to go 1 times d2, that's the derivative of the second function, plus 2 d1, so that would be the derivative of the first, that would be 3x squared. A little bit of cleanup work here. Of course, this x cancels with 2 of those. So we'd end up, or excuse me, it cancels with 1 of those, leaving you with 2. So it'd be x squared plus, I would probably rewrite it like this, 3x squared ln of x would be a pretty typical way of doing that. All right, hopefully you're doing well. Number 5 now, and as mentioned before, this is certainly the most complicated one yet. Okay, so the key here is remembering this, that the derivative of ln of u equals 1 over u times u prime. It just so happens with number 5 that this is one of those double composites where you have a function inside a function, and then that's inside, that whole thing's inside another function. So here's how this one looks. This right here is going to be my first u. Make sense? So, the derivative of ln of u is 1 over u. So we see that, that's 1 over u. But now we have to multiply by u prime. So, the derivative of ln of x squared is 1 over x squared. But now what's interesting, perhaps, is that u kind of switches. Now, the most inside function is x squared. That was inside ln. So we do have to multiply by the derivative of the inside there. So the derivative of x squared is 2x. Since it's a double composite, we're going to have 3 links to the chain rule here. So obviously a little bit of simplifying to be done here. I'm seeing 2 over x times ln of x squared. Okay, number 6. Once again is a situation where we have ln of u, and u is kind of complicated. So the derivative of ln of u is 1 over u. So that would be 1 over x times ln of x. But now we have to multiply by the derivative of what's on the inside. That's x ln x. So we go 1 d2 plus 2 d1. So I'm seeing these cancel. So I'm seeing 1 plus ln of x over x times ln of x. Okay, I am going to skip the section on logarithmic differentiation. It's not anything that I cover on my tests or quizzes. It is not covered on the AP test either. Nothing wrong with it. It's actually a pretty handy thing. But at this point, I want to give you what you need, and that's it. So one of the things you might notice about example 8, of course, is the use of absolute values. And often that causes, people some concern, like, oh my goodness, what am I going to do with that? Well, the truth is that ln, in and of itself, is undefined for negative numbers. It's only defined for positive numbers, as evidenced by that graph we saw earlier. You'll see this expression a lot. The only reason why you will see that is so that the negative numbers can become part of the domain. Because obviously if you take the absolute value of a negative number, the output is a positive number, and therefore you could take the natural log of that. So it doesn't really change how we do the problem at all. All right, so if we were going to do this problem, all we do is we'd say the inside function is cosine of x. That's ln of cosine of x, the derivative of ln. All right, let me use a little better notation in this. The derivative of ln is 1 over u, so that would be 1 over cosine x. Then we have to multiply by the derivative of what was on the inside, so that's negative sine x. So if you wanted to clean this up a little bit, you'd get negative sine x over cosine of x. Well, if you remember your trig identities, actually, it's negative tangent of x. So for those of you mathematicians out there, it's kind of a fascinating thing that the derivative of ln of cosine of x is equal to negative tangent of x. And if you take some other calculus courses later on, you'll look for sure at the reverse of this pattern, that the integral of negative tangent of x, the integral, right, would be ln of cosine x plus c. So it's just kind of a fascinating combination of different functions, ln, cosine, and tangent, all combined together into one. All right, so that's all we're going to cover for section 5.1. I think I will push ahead to do section 5.2. So we're going to kind of flip this around now. In section 5.1, we were talking about derivatives of ln of x. In section 5.2, we're going to look at not at integrals of ln, but we're going to look at integrals that lead to ln. So based on what we just did, this shouldn't be too hard. If the derivative of ln of x is 1 over x, well, the integral of 1 over x would have to be ln of x. And I'm going to write it like this with the absolute values. You'll see that very commonly, and then don't forget your plus c. And again, remember, the absolute values simply are allowing us to have positive and negative inputs. That's all it is. It doesn't really affect how we do the problem at all. Okay, and then of course, if we had this in composite form, kind of the reverse of the chain rule, this is something you got to be really careful of. This is a pattern you need to be very, very good at. If you see a fraction and the numerator is the derivative of the denominator, right, u prime over u, and the integral of that is simply ln of u with the absolute values in there plus c. So we will look at this pattern a lot. The bottom line, the pattern is this. If you have a fraction, if the derivative of the bottom is in the top, or something that we could turn into the top, then the answer to that integral is going to be ln of u plus c. Okay, let's do some examples. Again, you are highly encouraged to attempt these on your own, and then watch the video, work along with the video then to make sure that you have it. It's not as beneficial for you just to sit and watch the video. It's not bad. Best thing would be for you to try these. Here we go. All right, so number one, the first thing I would do is I would take the 2 out. If you take the 2 out, you can take any constant out. End up with this. And so, of course, the integral of 1 over x is just ln of x plus c. And the 2 that was there is still there. So 2 ln of x plus c. Hopefully this isn't too big of a jump. If you remember your log rules, if you were multiplying the log by a 2, you can actually move the 2 up onto the x. So you'd get ln of x squared plus c. And at this point you might protest and say, well, gosh, there was absolute values there, and then you moved the 2 up, and now the absolute values are gone. Well, remember, the absolute values are there simply to expand your domain beyond only positives, right? Well, what does squared do to any input? Doesn't it turn it into a positive? Of course it does. And so, because the squared is there, the absolute values are just unnecessary. It's not that they canceled out or anything. Okay, although if you did include them, it wouldn't be wrong. Number 2, I'll take a slightly different course with number 2. Again, you have a fraction, and you'll find pretty quickly that differentiating fractions, integrating fractions can be a big challenge. So here's what I want you to notice. We have a fraction, for one. But do you notice how the derivative of the bottom is the top, right? The derivative of 4x minus 1 is 4, and there it is. So what this does is perfectly fit the pattern of integral of u prime over u. It perfectly fits that. So if you remember, the integral of u prime over u is ln of u plus c. So I think this perfectly fits that pattern. And so I think the answer is ln 4x minus 1 plus c. You might have some questions about that. You might say, well, I don't think that's right. I don't think that that is the answer. Well, what you can do then is, of course, you can check this by differentiation. So just once, let's do that. The derivative of ln 4x minus 1 plus c. Well, the derivative of ln is 1 over u, so that would be 1 over 4x minus 1 times u prime, and that's 4. And then, of course, the derivative of any constant, like the c there, is 0. So this ends up being 4 over 4x minus 1. So we have checked this by differentiation because those two match up. So I would say that this, for certain, is our answer. Now something we'll look at in the near future is if this 4 was not a 4, let's say it was some other constant like a 7 or a 10 or 9 or whatever, then we might have to make some adjustments by either using u substitution like we practiced in or chapter 4, section 5, I think it was. Or you could also think of it as, where Timmy has messed up the chain rule and we need to fix it. Either way works, of course. So I think we'll see one of those here in a little bit. All right, so lost it. Let's go back. Let's take a look at number 3. Okay, so again, you have a fraction. This is probably important for me to say at this point. Not all fractions integrate to be ln, right? Not all fractions do. It just so happens that most, if not all of these, will, because it's in the integral of 1 over u section of the book. So be aware that you do have to recognize the pattern. Just because it's in that section of the book doesn't mean you're actually learning it. Focus on the pattern. Okay, so again, we have a fraction, and do you notice that the bottom differentiated is the top? So this maybe could be, this one's a little more complicated. You might want to set this up. You could say u equals x cubed plus x, so u prime would equal 3x squared plus 1. So you can see that the derivative of the bottom is right there in the top. So I think that this perfectly fits the ln pattern. So this would be ln of x cubed plus x plus c. You can check that by differentiation, and I think you'll find that it does work. Okay, number 4. Number 4 is a little deceptive. Notice that number 4, once again, is a fraction. Anytime you see a fraction, I think ln is at least worth considering. Hopefully you're seeing that pattern, and how many times I've said it as well. So we got the fraction here. Let's check this to see if this fits the ln pattern, the u prime over u. So u would have to be tangent of x. And what would u prime have to be? Well, hopefully you remember this from back in chapter 2, I think it was. Derivative of tangent is secant squared. So once again, this perfectly fits the pattern. So I would say the answer to this integral is ln tangent of x plus c. And again, notice I am putting in the absolute values. I'm not saying it, but they're there. All that does is that expands our domain from only positives to also including the negatives. So 5 is where things start to get a little more interesting. Again, feel free to try these on your own. I think that would be a valuable thing for you to do. And then go ahead and hit play again when you're done. But let's look at number 5. Once again, what do you see? Do you see the fraction? Of course. Anytime you see a fraction, you need to at least consider ln. It won't always be ln, but at least consider it. So let's consider that seriously here. If we're looking for the u prime over u pattern, u would have to be x squared plus 2x, right? That's the bottom. And then u prime would be 2x plus 2. Well, of course, this is where it appears maybe we've hit a little bit of a roadblock because the top is not u prime. The top is x plus 1. So what you're encouraged to notice here is that the top is only off by a factor of 2. So I'm allowed to fix that. So what I'm going to do is I'm going to multiply the top by 2. I'm going to do that. I need to multiply the outside by 1/2. Once I've done that, this does perfectly fit the u prime over u pattern. So the answer would be 1/2 ln x squared plus 2x plus c. A number of ways that could be manipulated, but I think that that's fine to leave it as is for now. Obviously, this could be checked by differentiation. If you wanted to do the full-on u substitution, certainly could. Maybe we'll do that with number 6. Okay, so take a look at number 6. A little simpler. Same concept, though. Once again, fraction, right? So the integral of 1 over 3x plus 2. So let's think this through. The derivative of the bottom has to be in the top if this is going to fit the u prime over u pattern. So u, let's do u substitution. Let's just do this officially. U would have to be the denominator, so u would be 3x plus 2. Du would be 3 dx. So when we attempt to integrate here by substitution of u, u is equal to 3x plus 2, so I'm saying 1 over u, and du equals 3 dx. So to make this work, we're going to have to divide both sides by 3. So we're going to get dx equals du, and then I will put the over 3 out front. So as you can see, this perfectly fits the u prime over u pattern now. So it would be 1/3 ln of u plus c. And whenever you do u substitution with an indefinite integral, you've got to plug back in. So it would be 1/3 ln absolute value 3x plus 2 plus c. That could be done by just kind of gauging the error in the chain rule, fixing by a factor of 3, or you could do u substitution like I just did there. Okay, let's apply this to finding area. Number 7 says find the area of the region bounded by the graph of y equals x over x squared plus 1, the x-axis, and the line x is equal to 3, which of course is a vertical line. You can check this out on your own if you want. The graph of x over x squared plus 1 looks approximately like this. And so we are asked to find the area of the region bounded by the graph, the x-axis, and the line x is equal to 3. So, x equals 3 being a vertical line, we're just going to say is right about there. So it's not the greatest worded question. At this point, let's just consider the area that they're describing to be that area right there. We do cross through at the origin there. Your x-intercept is there at 0. So setting this up, the area, let's use letter A for that, is equal to the integral from 0 to 3 of x over x squared plus 1 times dx. Okay, so once again, we're attempting to integrate a fraction. So whenever you're trying to integrate a fraction, it is certainly worthwhile to consider ln as a possible solution. So I'll just kind of work through this one. I won't do official u substitution. The bottom, the denominator there would have to be u, so it would be u equals x squared plus 1. So u prime would be 2x. If you notice, the top is not 2x, so this does not perfectly fit the u prime over u pattern. However, it's very easy to make it fit that pattern simply by multiplying the top by 2 and multiplying the outside of the integral by 1/2. Now it does perfectly fit the u prime over u pattern, so I feel very comfortable in saying that the integral there would equal ln of x squared plus 1. And then, of course, this is a definite integral, so we need to evaluate from 0 to 3. Just a quick side note, a lot of folks, I know we've talked about this in the previous chapter, a lot of folks get a little stressed about this 2x. Where does it go? It appears to disappear, right? Looks like it does. But remember, whenever you're integrating something that came from the chain rule, the derivative of the inside is integrated back to the inside. So in other words, it's put back in by reversing the chain rule. Okay, so let's use fundamental theorem part 1 with limits of 0 to 3. So that's going to be 1/2 ln of 10 minus 1/2 ln of 0 squared plus 1, so that would just be 1. Remember your ln stuff. Ln of 1 is 0. Be 1/2 times 0. So let's say a good final answer here would be area equals 1/2 ln of 10. You can manipulate that a little bit, but I think that's probably good enough form there. All right, so that takes us up to section 5.3, which I will cover in another video.